This question is about standing waves, and it is testing that you understand one of the equations that you're actually given on your data and formula sheet. So I brought up the data and formula sheet on the screen, and you can see that in the waves section you're given the equation for the first harmonic, and you're told that the frequency of the first harmonic is equal to 1 over 2L multiplied by the square root of T over mu. So it's requiring you to be able to use that equation, to be aware that equation exists, and then be able to use that equation correctly to be able to answer this question. So looking at it, we're told that we've got two strings. They both have the same first harmonic. So then we're asked for the conditions of these so that both strings have the same. So some of the properties of the string are changed, the length of the string is changed, and the diameter of the string is changed. So if I use the equation, so it was that the frequency is 1 over 2L multiplied by the square root of T over mu, and you need to be aware that L is the length. That's fairly straightforward. T is the tension within the string, and then mu is the mass per unit length. And that's the sort of only tricky bit within this. So the mass per unit length is given there, and it's the square root of the mass per unit length as well. So what we've got then, we're asked for the length and diameter required for the second string, so they both have it. So the first string, length L, diameter D, and then we're asked for what would that be for the second string. So if the length is the same, then the mass per unit length needs to be the same. So the tension is the same in both strings, we're told that. So if the lengths are the same, then the mass per unit length needs to be the same. This mu value needs to be the same. And the only way that can happen is if the diameters are the same. So if you've got the same length and the same diameter, well, it's the same string, so that's not really helpful. So it can't be either B or D, because if it's the same length, then neither of those giving us the same mass per unit length. So we then look at the other possibilities. Well, if you increase the diameter, then because the cross-sectional area is given as pi r squared, well, that's pi d squared over 4. So the cross-sectional area is proportional to diameter squared. So that then means that if you double the diameter, you quadruple the cross-sectional area, and that will quadruple the mass per unit length. But then we square root it. So that then makes things a little bit easier as long as you can get your head around those relationships. So our options are to double the length of the string for A. So if we double the length of the string for A, then the frequency has dropped by half. And then if we double the diameter, well, if we double the diameter, then we increase the mass per unit length by a factor of 4, then square root it. But that then reduces the frequency by a further factor of a half. So we make the frequency half as much and then half as much again. So A is wrong. And if you actually think about it, we've doubled the length of the string. If you play a musical instrument, you double the length of the string, and then you double the diameter of the string. A thicker string plays a lower note anyway, so we've doubled the length and we doubled the diameter. It doesn't make sense at all. So it's got to be, the only one it can be is now C, where we halve the length of the string and we double the diameter. Well, halving the length of the string doubles the frequency, because F is inversely proportional to L, so halving it doubles the frequency. And then if we double the diameter, then we quadruple the mass per unit length, but then it's related to the square root of that, and those two cancel out. So the answer has to be C.